Hello everybody. This lecture is going to be about Hess's Law, which is a new topic to thermochemistry that we do not cover in honors chemistry. Before we get started, a quick reminder that you are not a photocopier machine, you are a note taker. So if you needed every single word in your notes, I would have printed it for you, right? I would have made a photocopy, but that's not what we need. We need to focus on taking our notes. You can always go back and add to your notes when you do your annotations. Remember, there's probably a lot more words on the slides than needed. That way you can go back to the slides and use them for studying purposes. So please make sure that you're focusing on taking good notes, not trying to copy every single thing down. Here's the target to write down. I can use Hess's Law to calculate the unknown total enthalpy change during a reaction by adding together individual baby steps that I do know the enthalpy change for. Hess's Law is basically a puzzle. We're going to be trying to put together information we know to help us figure out something we do not know. Now here's the thing about puzzles. Sometimes a puzzle's very easy, like this top picture here. Sometimes the puzzles are not so easy, like this terrible one on the bottom. I don't know about you, but I feel like doing this white puzzle down here with all these crazy shapes would be pretty tough. So one of the things I think can be very helpful is if you're on a really tough one and you're pretty stuck, just remind yourself that you're looking for the puzzle pieces that need to go together. I don't have a lot of tricks for how to figure out which part of the equation to start with. If I did, believe me, I would tell you the trick if there was one. You'll notice that as you do more and more of these, you'll start to get faster at them. Your brain can kind of be trained to put the puzzle pieces together better. Sometimes you'll have nice whole numbers. Sometimes you're going to have some pretty ugly fractions. If you get stuck, my best advice is to stop, erase it, and start it over. Sometimes you need that clean slate and you realize it was just a simple adding error, or you didn't notice a subscript or something like that. But just remind yourself that even if it's feeling pretty tough like the one down here, it's still just a puzzle that you're trying to put together. The other thing I highly suggest is using pencil. You're going to need to erase. Use lots of binder paper. Do not squish your work. Don't write teeny tiny microscopic handwriting. Use as much binder paper as you need to help your brain keep organized and be able to get through this stuff. And lastly, you have to ask for help if you need it. You gotta ask early. You gotta ask often. You gotta be brave to say, I don't know how to do this. I need some help. Really, really important. So Hess's Law says in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So because it doesn't matter what pathway, what set of steps you use, if I do not know what the values for some of these arrows are, what some of these enthalpy values are, but I do know the others, I can use simple algebra and add them together and subtract and things like that to figure out the unknown part. And so that's what we're going to be focusing on. Real quick, you may have noticed I started using a word enthalpy instead of energy, and sometimes that makes people feel a little confused. So let's talk a little bit about what enthalpy is. Enthalpy is related to energy, but it's a little bit more complicated than what we typically think of. So enthalpy takes into account any change in pressure and volume. So if E equals the energy we're used to talking about, enthalpy would be that energy plus a pressure volume component as well. Now, the nice thing about this class and most scenarios is that we are not performing our reactions at really high pressures. we are not performing them at crazy changes in volume. So that PV component ends up being negligible. I don't have to worry about it. So just from a practical standpoint, we can assume that the enthalpy and the energy are the same thing. It's important for you to understand that they're not technically the same, that we are simplifying things a little bit, but we won't have to take into account any correction values to, make all of our work a little more complicated. We don't have to worry about that. So as long as our pressure and volume aren't undergoing crazy changes, we can be a little bit more simple in what we do. So if you look at this diagram, we have a couple pathways here. We have our reactants, we have our products. You can either get to the products on this green line, or you can get to the products using this crazy blue zigzag line. The analogy I like is path A is me, Mrs. Farmer, trying to clean the house. I try to take as few steps as possible. I try to be systematic about it. Compare that to path B, which is Mr. Farmer trying to clean the house. He takes 500 steps and, instead of taking one trip, he takes 50 trips and, back and forth and all over the place. Regardless of the path taken, you end up at the same place, right? Path A may be a much better choice than path B, right? But you're going to end up with the same result in the end. And that's an incredibly important concept for Hess's law. When we are calculating the enthalpy change, the energy change, we are literally only caring about products and reactant levels being subtracted here. All of this pathway stuff does not matter. So if I don't know how long path A is, but I can figure out path B, I can use that information to help me. So, one of the things that we do sometimes is we manipulate our enthalpy values because we're manipulating our equations. Because the steps to get from reactants to products don't matter, what we're going to do is we're going to combine steps we know. Maybe we multiply things or divide things to try to get calculations that add up to give us the starting and ending places that we want. So if I multiply a reaction in order to change the coefficients, what I have to do is I have to multiply that enthalpy by the same factor. Enthalpy depends on the quantity of material. So if instead of 1 mole of something, I have 2 moles, my enthalpy is going to change. So you can see here, if I have 1 mole of carbon, 1 mole of oxygen gas to make 1 mole of carbon dioxide, this is the amount of energy that's involved. But instead, if I had 2 moles of carbon, 2 moles of oxygen, 2 moles of carbon dioxide being made, I'm going to get twice that amount of energy being released, which makes sense. I have twice the material. That enthalpy is extensive, right? It's an extensive property. The quantity of material matters. We have more bonds being made and broken. We're going to have more energy being transferred. So I can use that multiplying trick to adjust my coefficients when I'm trying to piece my puzzle together in a little bit. Another thing you can do is you can reverse a reaction. So let's say I look in my data chart, in my appendix, and I have this reaction here. But the reaction I'm actually interested in is the reverse. I don't want carbon dioxide being made. What if I wanted carbon dioxide being broken apart? So what I can do is I can flip this reaction, and then instead of the energy being released, the energy would be absorbed. So when you reverse a reaction, you flip the sign. If it was negative, now it's positive. If it's positive, then it would be negative because you're going in the opposite direction. So these are 2 tricks that will allow us to manipulate our baby steps with known enthalpies to combine them into the reaction we actually care about with an unknown enthalpy. One thing that's important to know is that we use a term called standard state. So the standard state is the state of a material at defined set of conditions. So the standard state for a pure gas would be 1 atmosphere of pressure. A pure solid or a liquid, it would be whichever format, whatever form is most stable at 1 atmosphere of pressure and whatever temperature we're interested in, which is typically 25 degrees. You'll see the appendices are usually made at that temperature. If it's a solution, we assume that the standard state is 1 molar concentration. Standard conditions, standard state is important because that allows us to know for sure, what temperatures and what pressures were being used. When we look in those appendices, we want to make sure we're comparing apples and apples, not apples and oranges, right? So they're just what people agreed would be the standard state of a material. So the standard enthalpy change is the change in enthalpy when all of your reactants and products are in that standard state. If you notice, there's a little degree symbol up here. That little circle is telling you that you're using standard conditions and standard values. You can have enthalpies that are not at standard conditions. You could have something that's at, 47 degrees or 1.4 atmospheres. But then things get a lot more complicated, right? Then whatever appendix you have in the back of your textbook may not work. You may need to go find different charts to use to get your numbers. So that little symbol, that standard change, those standard conditions, makes our life a lot easier. If it's not standard conditions, it's not standard changes, then leave that little degree symbol off. Another thing that's important to pay attention to is that when you're doing enthalpy of formation calculations, when you're trying to determine how much energy is involved during a chemical reaction, by definition, we say that that enthalpy of formation is the energy for 1 mole of product being made. So we want to form 1 mole of something. Now, when we write and balance our chemical equations in Honors Chem, you're taught that you should always use whole numbers. You should not use fractions. Problem is, that's now going to be a little different. Okay, remember, now we're going to be able to use some fractions because we need to adjust our equation so that we are forming 1 mole of a substance. So when I look here, this is how you would normally write the formation of water. You would say you need 2 hydrogen molecules, 1 oxygen molecule, and it would make 2 water molecules. This is the amount of energy that would be released when you form those 2 water molecules, 2 moles of them. Problem is, because this is 2 moles, that's not considered a standard enthalpy of formation. Do you notice I left off that little circle up here? If I want to write the standard enthalpy of formation, I have to rewrite this equation so that I only have 1 mole of water being produced. Like that. So you can see here, in order to go from 2 moles to 1 mole, I got to divide by 2. That leaves me with this fraction over here. And for our purposes, that's okay. You'll also notice I had to divide my energy by 2, didn't I? So it's really important that if you're ever asked to identify which of these might be the standard enthalpy of formation reaction, what you need to do is you need to look for elements in their standard states. These would be gases, right? Combining to form 1 mole of your product. In its standard state, this would be liquid. Really important that from now on, we start paying a little more attention to the phases. You can see here, I didn't add the phases even though I should, right? Because we need to know that they're in their standard state. If you have a pure element, like hydrogen gas, oxygen gas, the enthalpy of formation of those is 0 kilojoules. If it's already in that form, it's not going to take any energy to make it be in that form, is it? If hydrogen is coming naturally as a gas at 25 degrees, I don't have to change it, do I? So it's not going to take any energy to put it in a certain form under those standard conditions. That is a fact that you have to memorize. You're not going to be told that on an exam. You're going to feel like numbers are missing from your chart because College Board is assuming that you can remember hydrogen and oxygen are both 0. So make sure you don't forget that pure elements count. Those diatomics count as pure elements. So you could have a chunk of solid calcium, that's a pure element, but so are your diatomic gases. Always double check though, weird ones like iodine, right? Bromine, those are not always gases under standard conditions. So pay attention to those little details that you'll come across in things like your warm-ups and your homework and things like that. Okay. So I'll show you now how we can put this all together. Okay. We want to know how much energy is involved when we combust methane. So there's your overall equation for combusting methane, right? You need some oxygen gas. You're going to make carbon dioxide and water. It's a nice balanced equation. Because we're trying to use standard values, right? We're going to want 1 mole. This is some information that's in a chart that you're given. It's given to you, in the appendix. It's given to you on a reference sheet. It's given to you as a chart in a word problem. You will be provided this information. You're not expected to know it. So, step 1 of this process is we're going to try to build this overall equation by adding up these equations. These are baby steps that we know the answers to find the big equation we don't know the answer to. So step 1, we need the methane on the left side. It needs to be a reactant. So I look over here and I see, hey, equation number 1 has methane. But it's a product. That's not good. But I am allowed to flip my equation. If I flip this to make methane a reactant, I have to change the sign on delta H. So instead of being negative 74.8, it is now positive 74.8. It is going to be incredibly helpful if off to the side you have some way of telling people what you have done. If you look, I took the opposite of reaction 1. On the AP test, you have to justify what you're doing to these equations, and just simply writing opposite of reaction 1 is good enough, okay? Next, step 2. If I look at this, carbon dioxide needs to be a product. Well, look here. Reaction 2 has carbon dioxide as a product. I'm just going to put that equation in next. I don't have to flip it. I don't have to multiply it. I don't have to do anything because it's already set up with carbon dioxide as a product. That was just regular old reaction 2. There was no transformation. Now, step 3. We need water as a product, don't we? If I look at reaction 3, I have water as a product. But look, I need 2 waters, don't I? I only have 1 in this reaction, so I need to multiply it. If I multiply the water by 2, all the other coefficients get multiplied by 2, and the enthalpy change gets multiplied by 2. I have double the material. double the energy. So here it is, multiplied by 2. I now have 2 hydrogens, 1 oxygen, and 2 waters. And they have 2 times that enthalpy. If you noticed, I left the oxygen till the end, didn't I? I didn't do anything because that often will work itself out towards the end of a problem. So some of the things that you'll learn when you practice are that some elements tend to be easier to balance than others, right? So it just becomes a little bit of a game on how you like to approach these puzzles. What order do you like to do them? So now what we have to do is we have to cross out things that show up on both sides. And then we're going to add up all these enthalpy values because the overall reaction is a sum of all the baby steps, right? I don't know how to do this in one giant step, but I do have data that lets me break it into baby pieces. So if I look here, I have a carbon and a carbon on each side. Those go away. I have 2 hydrogens and 2 hydrogens. Those go away. And I'm not seeing anything else that cancels. Add this all up, and you should notice that the final equation matches what we were after, doesn't it? And now I know that 890.36 kilojoules of energy is released when 1 mole of that methane combusts. Something I did not know before. My chart, my appendix, did not have this reaction in it. It only had baby steps. And I puzzle pieced them together until I could figure it out. All right, practice problem for you. Why don't you give this one a try? We want to know what the enthalpy is going to be of this reaction here. We don't know the answer, but we have some data for baby steps that we might be able to manipulate to get our final answer. Why don't you pause it and see what you can do to transform these reactions? Remember, you can add them together, you can multiply them, you can reverse them. See if you can figure out how to put them together into what we're after. Pause so you have time to do that. All right, let's see how it went. I'll show you what the answer is and how I got it. You should see that negative 103.4 kilojoules, right, is your answer. That means 103.4 kilojoules are being released. Remember, you either need to use the word released or you have to have a negative sign there. You have to be very careful about that. We care not just about the size, but also the direction, right? We need the magnitude and the direction this energy is going. So the way I did it is I looked and said, okay, I'm trying to get this as a reactant. If I flip reaction 2, it will be on the correct side. But I need 2 moles, and this only shows me 1 mole, so I'm going to have to multiply it by 2. Then I'm trying to get nitrogen and oxygen to be products, so if I take reaction 1 and I flip it, they'll be on the correct side. So that means I need a negative sign, right? But then, since these were those standard conditions trying to make 1 mole, and that leaves us with these fraction coefficients, that's not going to work because I don't want 1/2 of nitrogen, I want 1 mole of nitrogen. So I'm going to have to multiply that by 2 as well. So I do -2 times this value, -2 times this value, add those together, cancel out anything that shows up on both sides, and I get my overall finished answer. I did not know the enthalpy change for this reaction. It was not in my appendix. I didn't know what it was, but my appendix had some baby steps that I could combine, and that's what I did. Okay? Let's try another one. This has 3 reactions this time. A little bit trickier. Give this one a try. Pause the video if you need some more time to figure this out. All right, I'm going to show you what I did. One thing I want you to remember is that if you combine things in a different order or in a different way compared to me, that's fine. Remember, 1 plus 2 and 2 plus 1 are the same answer. And so please do not get stressed out if you did things in a slightly different order than me. It's just going to depend on what your brain notices and the route that you take. So pause the video if you need another minute or 2 to solve this. All right, I'll show you how my brain did this problem, how I figured out the puzzle. So I get negative 11 kilojoules. I start with reaction 3 because I want to get my iron oxide on the left. Reaction 3 has this iron 2 oxide, but it needs to be flipped. It's on the wrong side. The other thing I notice is that I'm only wanting 1 mole. My chart told me about 3 moles, so I'm going to need to multiply by 1/3. I multiply all my coefficients by 1/3, and then I also multiply my enthalpy. Negative because they flipped it. Next, I want to try to get iron on the right. So if I look, reaction number 2 has iron on the right-hand side, but there's 2 moles. I only want 1 mole. I'm going to multiply by 1/2. If you notice, I do not have a negative sign in front because I'm not flipping it. I'm just multiplying it by a value. Lastly, I have a big giant mess to clean up, don't I? Lots of things need to be, crossed out, combined, things like that. And if I look, I have Fe3O4 over here, which needs to go away. It's not in my overall equation. So I need Fe3O4 on the left to be able to cancel those out. I have 1/3 here, so I'm going to need 1/3 here. But what's tricky about reaction 1 is that there's 2 moles. How do I go from 2 moles of something to 1/3 of a mole? I have to multiply by 1/6. This is where being comfortable with fractions comes into play, right? I'm hoping you practice those in your math class a bunch. So remember, you can do things with the denominators and change them around and all of that, but you need to be manipulating those fractions. So in order to go from 2 moles to 1/3, I got to multiply this by 1/6. So if I do that, these are the coefficients I end up with. Now if you look, now lots of things cancel, don't they? This Fe3O4 will cancel, this Fe2O3 will cancel. Now I'm left with carbon monoxides and carbon dioxides. If you look, you gotta kind of start combining them around. But when you're done, they all cancel out. You used a lot of horrible little baby steps. You manipulated them in crazy ways, and that allowed you to figure out how much energy would be released through the equation that we were interested in. Okay? Now, typically at this point, everybody's head is on the desk, or they're groaning, or their eyes are bugging out, all stressed out. Yeah, it is a mess, isn't it? It's a giant puzzle. Some people love puzzles. Some people hate puzzles. Some people see patterns. Some people don't. Some people love fractions. Some people hate them. If you love it, awesome. You got an easy topic. If you hate it, I'm sorry. Do a little extra practice, but you'll get there, right? Not everybody has the same strengths and weaknesses. Do however much practice you need to get good at it. One thing I highly suggest is that you do not crowd and squish your work. This is a game of record keeping. you're going to need to be very careful that you don't lose track of any little coefficients here, any little fractions. So you want to make sure that you're using enough binder paper that your brain can stay organized and calm, okay? Now just one little thing I threw in here at the end, because we're seeing it show up more and more recently on the AP exam, and the way that College Board is starting to format some of their units. Now, usually you will see on formation values, enthalpy values, kilojoules or maybe kilojoules per mole. College Board kind of seems to have invented their own unit that at first a lot of teachers thought was pretty wacky. They started using something called kilojoules per mole reaction. That little subscript there, they've started using all over the place. Now, it kind of makes sense once we started playing around with it. Once we started doing more of the practice problems, we noticed that when we format things using this kilojoules per mole reaction, we started to see fewer mistakes from students on their dimensional analysis. We were kind of doing a little shortcut in our head with our unit conversions, and I think College Board thought, let's formalize this and try to prevent some of these common mistakes on these dimensional analysis questions. Because you're going to be doing things like reaction with a coefficient of 1s, and then maybe sometimes you double it and now you have 2s and things like that, we really have to start thinking about the reaction as an entire unit. Kind of like if you're going to make cookies and you want to do the recipe once, or do you want to double the recipe? Well, you may need to know how much of your, ingredients you need for one batch versus 2 batches. So I think that's kind of what they were thinking, is how can we get kids to think of the chemical equation as an entire batch that has to be done at once. So let me try to show you an example here. Let's say we have our formation of water again, and we want to know the energy released if you had 100 grams of oxygen to start with. Now, instantly from Honors Chem, you should know if you have grams, you should get to moles, then you can start doing your actual stoichiometry, right? So I'm going to go from grams of oxygen to moles of oxygen. And then I'm going to think of this equation as one whole packaged unit, one batch, one run. I'm going to do this in one go, okay? If I do this reaction one time, I need half a mole of oxygen. So you can see here, if I do the reaction one time with the moles that are listed, I have to use a half mole of oxygen. And I can see here that if I do this reaction one time with the moles that are listed, it's going to release 286 kilojoules of energy. And what's nice is you can now see I can formally cancel the units properly and be left with just kilojoules, which is really what I should be left with. Now, personally, I don't really care if you use this format. Sometimes you will see me do it even slightly differently, where instead of saying mole reaction, I may just even write one reaction. One reaction, I needed a half a mole. One reaction gave me negative 286 kilojoules. It's the same concept, okay? Even that, if you can just use your coefficients properly and do proper dimensional analysis, they are not going to mark you wrong. They will still give you credit. But I will tell you, having done this for a long time, I think if you can get in the habit of using the units the way College Board intends, you're going to end up doing better. You're going to make fewer mistakes. They are purposely phrasing their questions in such a way that this unit conversion method ends up working in your favor, okay? And because we're in an AP class and there's the AP exam and it's College Board deciding how it's graded, we need to kind of be doing it the way they like, okay? So try using this kilojoules per mole reaction. If you notice on worksheets and answer keys that I just did it the old-fashioned way, you don't need to constantly email me to tell me, okay? Just make sure you understand that one way is a little more traditional, a little old-fashioned. This is the newer way that College Board is liking to do it. Over time, I'm slowly trying to update things to match their new, preference for their units. So just kind of keep an eye out and try doing it the new way sometimes. So that's basically the end of this PowerPoint lecture. I do just want to come back full circle moment right to the beginning of the PowerPoint where I kind of talked to you about this being a puzzle. And I want to remind you and emphasize, you gotta tell your brain it's just a puzzle. Where are my puzzle pieces? Where do they fit together? Okay, so just keep calm, take deep breaths, erase it if you need to. Don't squish your work, right? We want to be able to count carefully. We don't want to miss any subscripts or anything like that. And ask for help, okay? You're going to hear me all year long say you need to ask for help early. You need to ask for help often. You need to be brave enough to ask for help, okay? Practice, practice, practice. You will get faster. Get a big eraser for this class, right? No shame in erasing and starting it over. All right, everybody, that is it. I hope that was helpful. Bye.